Okay, hi everybody. I believe it's Tuesday when you're watching this. So hopefully you printed out the notes that go with this screencast, and if you have not done that, maybe you'll do so now before you start. So this is our, let's see, second, I guess, new method of solving differential equations. I think I'd also say this is probably the first real meaty one, okay? What we're going to talk about today here are exact differential equations. And when we talk about exact differential equations, we need to have an understanding of something called a total differential of a function, which we kind of gloss over in AP AB and AP BC calculus, really because you don't need this notation. But it is important for us to go through this explanation of what a total differential is before we get into this next method of solving diff-EQs. So let's do this through a function of x, because this is probably our most comfortable lens of functions. Last year, when we looked at y equals x squared minus 1, we did this. We said dy dx equals 2x. And then a little bit later on, we started talking about error, and we may have multiplied both sides by dx like that. This is the expression or equation I want to focus on for a moment here. If you look at this for a minute from a graphical perspective, and we take a look at just a really rough sketch here of y equals x squared minus 1, oh my goodness, let me just fix that atrocious thing. Okay, sorry. So here's a parabola, y equals x squared minus 1. Please don't laugh, it looks awful. And then here's a tangent line, it's in blue, and here's a point of tangency. And last year, you remember talking about something called the local linear approximation. And the local linear approximation is the use of the tangent line to approximate the function value. So here, if this is the tangent line, we call this horizontal distance change in x. And you'll notice that if I'm looking at the change in x, I'm going to call this change in x. If I were to change in x in the positive direction, I'm just moving positively just for convenience here, the corresponding y value of the tangent line is very, very close to the y value of the function. And, you know, the whole notion of very close opens a can of worms, because who decides what's close enough? That introduces us to the idea of error, series, so on and so forth. But for now, the idea that I want to just make sure you understand is that when you change in x, when you horizontally displace from a point of tangency, what you arrive at, if you take the corresponding changes in y, are the y value of the tangent line, or the local linear approximation, and the y value of the function. What's important to understand and distinguish is that when you change in x, there are really two different changes in y. The change in y of the function is delta y. The change in y of the tangent line is dy. Similarly, the change in x of the tangent line we call dx, and the change in x of the function we call delta x. But as you can clearly see here, delta x and dx are the same. So when we start talking about dy is the total change in y of the local linear approximation. dy is the total change in y of the local linear approximation given a certain change in x dx, which is dx. Very nice, honey. That was very well done. Very pretty. Okay, let me finish, please, okay? Thank you, sweetheart. We can call this dy, but we can also call this the total differential. And the total differential, as you see, is none other than dy dx times dx, so to speak, right? Because dy dx is this after all. The total differential is dy dx times dx. Now, this total differential, again, means the change in y, or the change in the function f of x, by way of the local linear approximation, given a certain change in x dx or delta x. I don't know why this all just adjusted. And we can certainly write total differential. We can also write this. The total differential of y is dy dx times dx. Okay, just another way of talking about the derivative and really focusing and honing in on the idea of the change in the value of the function. Sorry, oh my gosh. The change in the value of y, which is the function, by way of the local linear approximation. And I have that written down at the bottom of the page here. So here, when I have dy equals 2x dx, probably our most comfortable narrative that we tell ourselves is the total differential of something is 2x dx. But what was that something? That something was none other than x squared minus 1. So now we can also say this is the total differential of x squared minus 1, which is 2x dx. Okay? So this total differential just means the change in the y value in the function x squared minus 1, the change in the function x squared minus 1 by way of the local linear approximation. Okay, let's extend this notion to 3-space for a minute. So here you have a graphic of a tangent plane. I think I have a bigger one for me here. Here it is. Yes, very good. Okay. So in 3-space, when we talk about functions, we're talking about functions of x and y, correct? And when we talk about the tangent plane, what we're saying is that any point near the point of tangency, and here near a point of tangency can be anywhere around the point of tangency, so to speak, right? Unlike in the two-dimensional world, the xy plane, close to the point of tangency is just to the left or to the right. Here, close to the point of tangency, it could be anywhere around point P. And as you can imagine, the change in z, if I were to change in z moving just in the x direction, well then certainly I'd only need to consider a change in x. If I was moving just in the y direction, I only need to think about the approximate change in z as a function of a change in y. But I have to allow myself the possibility that I'd want to change in x and y, right? So if I think, oh my goodness. So if I think about this, what I'm going to do here is on the tangent plane here, this tan plane, if I were to move in just the x direction, this distance, well, I would see that the z value would drop slightly, correct? And again, that new z value on the tangent plane would be a close approximation of the actual z value. However, if I wanted to move in the y direction on the tangent plane, my z value would be, it looks like here, if I'm taking this picture at least a little bit literally, it looks like here my z value is going to increase a bit. So my local linear approximation, that z value will be greater than the z value here. But what if I wanted to increase in x and in y? Well then what I'm looking at is, let's see, changing in x and changing in y. Now I'm looking at this, and the change in z here, so the change in z from P to this new point on the tangent plane would be a sum of the change in z by way of x plus the change in z by way of y. What that means is, in 3-space, if I want to talk about the total differential of f of x comma y, and let's write this in our new notation, the total differential in f of x comma y, which is conventionally referred to as z, is going to come by way of the change in f or z as a function of x dx plus the change in f as a function of y dy. Okay, and we may see it written this way. You know, sometimes you may see this written this way. dz equals the change in f with respect to x change in f with respect to y, dy, right? So once again, we're talking about the total differential being the approximate change in z by way of a local linear approximation. Okay, let's go back here and here we go. All right, let's find this total differential with this function here. Okay, all right, well, first of all, back in the day in multi, let's just kind of practice a couple of things. I may have thrown a couple of things at you. Let's just remember how to take partial derivatives. Okay, partial derivatives. All right, I'll meet you, or maybe you want to do it with me, whatever you'd like to do. 3x squared y plus y squared, yeah? dz by dy is going to be x cubed plus 2xy. Okay, if we're talking about the total differential, we're saying the total differential, the total differential is equal to, and I will say here that this one, when I use total differential, I just caught myself, goodness gracious, that should be not as curly z. The total differential of z will equal dz by dx, so 3x squared y plus y squared dx plus, here is dz by dy, x cubed plus 2xy dy. Now, I could leave this total differential this way. I can also say this is the total differential of, right here, that's what we took the total differential of, x cubed y plus xy squared equals 3x squared y plus y squared dx plus x cubed plus 2xy dy. Everyone okay? Very good. And here's where I wrote this out, okay? This is kind of the most important, this is like the critical idea statement. The total differential describes the change in the dependent variable by way of the local linear approximation, okay? As a result of changes or change, because if you only have one dependent variable, then it's just one change. But it's the change in the dependent variable by way of the local linear approximation as a result of changes in the independent variables dx or dy. Okay, before I move on to the actual lesson now, there's one thing that I want you to make sure you see. You probably see it very clearly here. Everyone here sees that when I write the total differential statement like this, it is abundantly clear to you, I think, that these two things here, the x squared minus 1 and the 2x, share a relationship. Yes, namely that this left-hand side is the antiderivative of 2x after all, right? That's where I started, up here. Similarly, the relationship between here and these, right? In this situation, this is the partial derivative of z with respect to x. This is the partial derivative of z with respect to y. Okay? That connection is going to become very, very important right now. Okay. So here is the thing. Once we know what this means, and that kind of detour into an explanation of an idea is really kind of critical before we move onto the Diffie-Q stuff. Once we know what this is, and here's an example of an equation in that form. Granted, here, notice here, the total differential of z here is set equal to 0, which we'll deal with in a second. But once we understand that this expression, and specifically this part of it right here, right? Because now we recognize that this means exactly where'd it go? Ah, here it is. I'm sorry. Okay. this and this are identical. Our task becomes then to figure out maybe what the z expression or the z function is that yields these two partial derivatives here and here. Because remember, we saw a connection here and here. Let's work this out very, very slowly. Well, I guess you could actually just slow me down to like 1/4 speed, but that, oh my goodness, that would be so embarrassing. So here is the question. This left-hand side is the total differential of some function of x and y. So we know that this piece here (3x² y plus y²), this is equal to the partial derivative of some function with respect to x. Okay? Similarly, this here, x³ plus 2xy, equals the partial derivative of some function with respect to y. Why? Because what we just talked about over here, right? When we went and found the total differential of x³ y plus xy², we saw that this, the factor attached to the dummy dx by way of multiplication, this was the partial derivative of this expression with respect to x. So the question is, if I know these two partial derivatives, can I take that left-hand side and figure out what function has these two partial derivatives? The answer is yes, okay? The first thing we want to do is we want to check to see if the diffie q is what we called an exact differential equation. Okay, here is the criteria of what an exact differential equation is. First, let me give you some symbols. In general, when you have a differential equation written in this total differential form, the expression that represents the partial derivative with respect to x is often referred to as function m, which is a function of x and y. Similarly, the expression that represents the partial derivative of some function with respect to y is referred to as function n, and n is a function of x and y. The criteria of a differential equation being an exact differential equation when it's in total differential form is the following. Okay, here's the criteria. Does the partial derivative with respect to y of the partial derivative with respect to x equal the partial derivative with respect to x of the partial derivative with respect to y? Okay, it actually sounds worse than it is, I absolutely promise. So let's check and see if this is an exact diffie q. We're going to take the derivative with respect to y of the partial derivative with respect to x. And what we get here is that this equals 3x² plus 2y. Okay, and we're going to take the partial derivative with respect to x of the partial derivative with respect to y, and look what we get. Okay, the fact that these two are the same means the differential equation is exact. We can proceed. Okay, here we go. Here is what we're going to do. I am going to choose, I'm looking at these two here, I'm going to choose the easier one, and in this case they're both equally simple or equally complicated, however you're feeling today. I'm just going to choose this one, okay? If I consider function m, don't forget, m is the partial derivative of the unknown function we're looking for with respect to x. Now watch. I am going to take the indefinite integral of m of xy. Now, I'm going to pause for a second and I want you to debate this. If m is the partial derivative of some function with respect to x, and I want to integrate m to get to that function, somebody tell me, or you duke it out, all of you, what the dummy here should be. Is the dummy dx or is the dummy dy? M here is the partial derivative with respect to x. And in integrating m of xy, I want to get back to the function. What is the dummy, everyone? Pause me here and all of you argue and just talk and then replay me. The dummy is x. Okay, when I integrate this with respect to x, I get x cubed y plus xy squared. Now, this is very important, plus c, but I'm not going to write plus c. I'm going to write plus a function of y, because if I'm anti-differentiating with respect to x, a function of y is treated as a constant. You understand? So this could be a function of y, like it could be, for example, y cubed. It could also be 7, but the number 7 is a function of y, and it's also it's a constant. So constants play both roles, but this is important. We need to account for the fact that in multivariables, if I'm integrating an expression in terms of x and y, two independent variables, if I'm integrating with respect to x, I have a potential f of y that is a constant, okay? And that constant could include like a number, an actual constant like 3, or it can include 3 plus y squared, etc., okay? All right. So let's make a little note. What is this? What did I just find here? This is my f of xy. You can't get lost in the story here. What you just found is your f of xy. We just found it. We found f of xy. It'd be nice though if we can figure out what this is, right? All right, now here's what I'm going to do. Now watch. I'm going to take the derivative. Oops, wrong kind of d. Pardon me. I'm going to take the partial derivative with respect to y of this. X cubed y plus xy squared plus f of y. Now, I know you know how to do this, to take the derivative. Let's do it together. X cubed plus 2xy plus f prime of y. But now here's my question to you. In taking this step here, when I found my f of xy, and then I took the partial derivative with respect to y, somewhere else in this picture, I have the partial derivative of this function with respect to y. Where was it? It was right here. So this, right, absolutely better equal this. Okay? All right. Oh, wait a minute. You know what? That's not the partial derivative with respect to y. No, the partial derivative, heavens beans, I didn't scroll up enough. Let's erase. It wasn't this one. It wasn't this one. It wasn't that one. It was, where is it? There it is. This was the partial derivative with respect to y. Okay, bring it all the way down. Here we go. Okay. X cubed plus 2xy. Very good. Now you see what's going on here. It just so happens that if you look over here, right, x cubed plus 2xy, x cubed plus 2xy. But interestingly here, f prime of y equals 0. So f prime of y equals 0. Which means then what, everyone? Yes, which means then y equals some constant. Like a constant, a traditional constant. Sometimes you'll have situations happening where a situation will occur where, you know, like I pulled down the partial derivative from the top. Maybe the partial derivative here would have been, there'd be like a plus 11, in which case you'd have f prime of y equals 11, right? And then y equals 11y, but that didn't happen here. Let's erase that. Okay? Now what this means here, let's go back. Let's go back. Where did I? Here we go. All right, so y is a constant, like a traditional constant, a number. We have to go back and figure out where is f of xy. Here it is, right? We left f of xy here. So at the end of the day, f of xy equals x cubed y plus xy squared plus some constant c1. Now, notice something, everyone. This was just the left-hand side of the equation. All we did, all that work, was to figure out, oh, that's so great. The left-hand side means it's the total differential of, where was it? There it is, x cubed y plus xy squared plus c1, just in case there's another constant that kind of floats around here, equals 0. All right. Well, what do I do here? How do I, how do I get rid of the total differential? Let's go back. Let's come back to the very beginnings. If I had this here, and if I had the total, well, that's a bad example. Hold on. Sorry, everyone. So sorry. If I was here, oh, maybe I didn't talk about that yet. Okay, my apologies. Come back over here. Where am I? Here we go. Okay. So now I want to just solve for, I would like to get rid of the differential. So here's what I'm going to do. I'm going to now integrate both sides. And what I get is the integral and the differential cancel. I get x cubed y plus xy squared plus c1 equals, antiderivative of a constant is just some other constant. I can absorb these two together, x cubed y plus xy squared plus c, or k, equals 0. And I have just solved the diffie-q. I'm pausing. I'm wondering what your faces all look like right now. Mrs. Green, if I would love to have like a picture of their faces. It's so long-winded, right? And you're constantly going back between a partial derivative, integrating, derivative, taking the derivative, integrating. Let's do one more, shall we? Let's just do one more together, okay? Go to the back before we get to the very last question here. This one gets a little bit more meaty. Let's just do another one together, shall we? Okay, let's solve this diffie-q. I'm gonna pull one off your homework here. Here we go. Let's do this one. Let's see. Let's do this one. You know what? Never mind. Just go to the last page because I just paused you and I tried to find one that was going to be, just, a little bit more interesting. And I think the most interesting one is this one. So let's just do this one, shall we? Okay. So here, I'm going to start us off. Here is it says find the unique solution given this diffie-q in total differential notation. We have an initial value problem now. So first, we're going to check to see if this diffie-q is exact. It is, right? So again, this here is the partial derivative of some function with respect to x. This here is the partial derivative of something with respect to y. Okay? We're checking to see if they are exact, which means we are checking the partial derivative with respect to y of the partial derivative with respect to x, and the partial derivative with respect to x of the partial derivative with respect to y. They are the same. The diffie-q is exact, so we may proceed. Here we go. I am going to, again, now here, this is really interesting. Would you rather, to get back to the f of xy, don't forget, to get back to the function, right? We're going to take the antiderivative. Would you rather anti-differentiate this with respect to x or anti-differentiate this with respect to y? I much rather would do this because this side would require integration by parts. Do you see? Very good. So let's take the antiderivative of the partial derivative with respect to x. And when we do that, here we go, right? And here, this is again, that is f of y. I think what I want you to do right now, this is still early for us, make a reminder to yourself. Make yourself understand that what you're finding here on the left-hand side is the function whose total differential is this, okay? We're just working the left-hand side. That way you don't forget it and lose it, because this work is very, very long. Okay, now I'm going to take the derivative of f of xy with respect to y. And when I do that, here is where I'm meeting up with you all. When I do that, I get x plus f prime of y. And don't forget, this here is the partial derivative with respect to y. Okay, but you know that this is the partial derivative with respect to y as well. So these two things must be equal. 2 plus x plus y e to the y. Very good. So in order for us to find in the end what f of xy is, we have to figure out what f of y is. That's the big unknown, right? Well, let's see. I see that x and x are accounted for here, but what is f prime of y? Well, f prime of y equals 2 plus y e to the y. Okay, so f prime of y equals 2 plus y e to the y. How do we solve for f of y? Yes, we are going to anti-differentiate. Oh, I guess we couldn't avoid parts after all. Poor you. This equals 2y. That's easy, right? Okay, I'm going to do this plus... Okay, I'm going to go over here and make a side note, and we'll just always swing right back. Integration by parts. Let's let u equal y. dv equals e to the y dy. That means du equals dy, and v equals e to the y. Great. That means this integral then equals y e to the y minus the integral of e to the y dy, which equals y e to the y minus e to the y plus c. Whew. Okay, so then that means f of y equals 2y plus y e to the y minus e to the y plus c. So that means the entire left-hand side. Where did I see? This is why I have to keep track of everything. Aha, here it is. So that means the left-hand side of this differential equation is the total differential of, right here, e to the x plus xy plus 2y plus y e to the y minus e to the y plus c. This all equals 0. Okay? And if I want to now undo the differential, e to the x plus xy plus 2y plus y e to the y minus e to the y plus c equals some other constant c1, or I can just absorb these two and 0 here and just call this constant k or something like that. Okay, equals 0. What was that initial point again? Oh my goodness. Y of 0 equals 1. Okay, so if y of 0 equals 1, then it must be the case that, let's plug in x for 0 and y for 1, right? So this becomes 1 plus 0 plus 2 plus, is that 1? Minus e plus k equals 0. So what does e equal? What does k? What does k equal? Let's see. 2, 4, k equals e minus 4. Oh my goodness. So at the end of the day, here is my solution to this Diffie Q. Plus, the constant is e minus 4. Boom. There it is. Okay. Do you want to try another one? Mrs. Green, please take a scan of the room. Are they okay? Is everyone all right? Again, please add questions. Oh, I bet your question is, I bet a number of you have a question about the situation here. Will the C1 and C2 always work out this way? Okay, you know what? Let's do another one, and then we're going to talk about that. I think you also probably all find this step a little bit slick, and I don't blame you. How do I make that a little bit more clean? Okay, but let's just let me think on that. Okay, let's try one more, shall we? And let's do this one. How about you do this one totally on your own, and then check me for the answers. Okay, let me find one that's going to be for sure. It's going to work. Let's see. 3D X. Oh yes, very good. Okay, ready to solve this one. So solve the Diffie Q. And remember, with these, I mean, you can imagine what's happening tomorrow, right? Tomorrow, we're looking at Diffie Qs in total differential form when they're not exact. So tonight's homework, your questions will ask you to determine whether a Diffie Q is exact, or it'll say, determine if the Diffie Q is exact, and if it's exact, solve it. So, you know, again, with differential equations, what gets difficult is when you have the totality of all the methods. But my point is, don't forget to check for exactness first. Okay, try this on your own with someone, and then check me for the answers. I don't know what I just did. I don't know if I just did that while I was, oh dear. Anyway, this is what I did. I ignore the yellow for now. I checked they're exact right here. And then what I did was I integrated dy because they were both equally simple. And I made a note to myself so I don't get lost. This is f of xy. I took the derivative with respect to x, and I got this. And this is where I want you to tend to the two yellows being equal, right? And then that means f prime equals x cubed, f of x equals 1/4 x to the fourth plus c, and etc. All right. Okay. Listen, if this is something that you want to just take your time with and just maybe talk it out as a class and do examples together for a day or two, just let me know. Or no, don't let me know because I won't know. But you'll go ahead and do that. Okay? All right. Goodbye.